So in this video we want to calculate the integral of the secant function. And the secant function, which we write sec of theta, is the reciprocal of the cosine function, which we can write as the cosine of theta all in brackets to the power of -1. That means this. And it should not be confused. This is not the same as the inverse cosine function. It is the reciprocal of the cosine. So as I've said, in this video we want to calculate the integral of this function. So we want to calculate the integral of 1 over the cosine of theta with respect to theta. And what I'm going to do is to calculate this integral on the next slide. So this is the integral that we want to calculate, which we're going to write this way. And initially it looks fairly harmless, but when we think about it a little bit, it's probably not immediately clear how to do this. So what we're going to do is use a series of techniques, and I think the first time you see this, if it's not obvious to you why we're doing it, that's quite normal. When we calculate something in mathematics for the first time, we don't always spot what the right technique to do is, and often we end up playing with things and using different techniques until eventually we recognize what to do. And it's really only with time and practice that we start more often going down the right route more quickly. So what I'm going to do here is I'm going to recognize that this is in the denominator, and I therefore don't know what to do with it, but I do have an algebraic identity that is very familiar, which is that I can write cos squared theta plus sine squared theta is equal to 1, and that follows from the definition of the sine and cosine functions. So if I want to use this identity, I'm going to turn this cosine into cos squared, and the only way I can do that is by multiplying top and bottom by cosine. So I can write my integral multiplying the top and bottom by cosine as cos theta divided by cos squared theta d theta. So what we're doing is we multiply top and bottom by cos theta. And then we can use this identity to write this as the integral of cos of theta divided by 1 minus sine squared theta integrated with respect to theta. Now when we look at the integral written in this form, and this is algebraically identical to its initial form, what we recognize is that here we have a function of sine of theta multiplied by the cosine of theta, and the cosine of theta is the derivative of sine of theta. So just to make that perhaps a little bit clearer, let me just split this up into two factors. We have 1 over 1 minus sine squared theta, and this is multiplied by the cosine of theta integrated with respect to theta. And when we look at the integral written in this way, this is a function of the sine of theta, and this is the derivative of the sine of theta. So what we do here is we recognize that we have an integral of the following form. So we have an integral of some function of a function of our variable theta, and the function u here is the sine. So we have a function of the sine of theta multiplied by du d theta, and du d theta in our case is the derivative of the sine of theta, which is the cosine of theta, and we recognize exactly this factor is here. And this function integrated with respect to theta can be rewritten using the chain rule as a function of u integrated with respect to u, and then having calculated the integral we replace u by u of theta. So that's the technique that we're going to use here, and this means that we can rewrite our integral here as the integral of 1 over 1 minus u squared with respect to u. So this follows just from using this formula with u being the sine of theta. And this can be rewritten in turn as the integral of 1 over 1 plus u times 1 minus u with respect to u. And when we see this, I hope that we think we should be using partial fractions. Now, this is a very simple case of partial fractions, so what I'm going to do essentially is to guess the answer, and to do that I'm first going to make a bit of room. So what I want to do now is to write the integrand here, 1 over 1 plus u times 1 minus u, as a sum or difference of partial fractions. And the partial fractions that I'm going to use are going to be 1 plus u, because that's one of the original factors, and 1 minus u, because that is the other of the original factors here. Now, if I add these together, I'm going to have the common denominator of their product, and that's perfect, that's exactly what I want. And then when I add them together, I'm going to get 1 minus u here, and 1 plus u here, and the u and the minus u are going to cancel, so that's very, very good. So I certainly want to put a plus sign here. But if I add the two of them together, I'm going to get the ones adding, so I'm going to get 2 instead of 1. I want 1 for my numerator because that's the original integrand. So what I'm going to do is I'm going to say I have 1 here, and I'll put a factor of a half outside. And now if I look at this, when I put this together, I'm going to get 2 over 1 plus u times 1 minus u, and the 2 and the half will cancel, so I will obtain this initial integrand. So that's what I want to substitute in to here. So our integral can be written as the integral of a half 1 over 1 plus u plus 1 over 1 minus u, with a half multiplying everything, integrated with respect to u. And these are integrals that you could do by a change of variable, but they're essentially straightforward and we can guess the answer, and I think we should always guess the answer if we can. So what we have here is a half, and then it is the logarithm of the modulus of 1 plus u, and then it is going to be a half the logarithm of the modulus of 1 minus u. And now when I differentiate this, I'm going to get 1 over 1 minus u, which is good, but multiplied by the derivative of 1 minus u, that's going to give me a minus sign, so I have to put a minus sign here. And so this combination is exactly this, and I can add here at the end an integration constant. So let me just pause here and make a little bit more room. So from this we see that our integral is going to be a half, that's a common factor, the logarithm of the modulus of, and now it's going to be 1 plus u divided by 1 minus u, where we're using the rule for logarithms, and a half is a common factor, so we'll keep it outside. So the top is 1 plus u, and the bottom is 1 minus u, end the modulus, and we add an integration constant. And now we recall what u is. U was the sine of theta, so therefore we have that our integral I is a half the logarithm of the modulus of 1 plus sine theta over 1 minus sine theta with an integration constant. And this result here is correct, but it's not the end of our story, because what I want to show on the next slide is that it is possible to significantly simplify this, and we'll look at that on the next slide. So just to summarize, what we did on this slide was we rewrote our integrand in this form so that we could use this identity to rewrite our integrand in this way, and then we recognized that this is a function of the sine of theta, and this factor of cos of theta in the numerator corresponds to the derivative of sine of theta, so we were able to use this technique. And then when we had this result, we recognized that this was something that we could use partial fractions on. This was our partial fraction decomposition, which we essentially wrote down. We didn't need to really solve for the constants here and here. And then these were straightforward integrals, which we are able to essentially guess what they are, and we can just check the answers by differentiating them in our heads. And then here we've used the rules for logs, and finally we always have to substitute back in terms of our initial variable for such an indefinite integral. So now let's simplify this. So on the previous slide we showed that the integral we're trying to calculate, the integral of the secant function, can be written as a half the logarithm of the modulus of 1 plus sine theta over 1 minus sine theta. And what I now want to do is to simplify that, and to do it we're going to again use our relationship that cos squared theta plus sine squared theta is equal to 1. And what we're going to do is we're going to multiply the top and the bottom by a common factor, because here we have 1 minus sine theta, so if we multiply the top and the bottom by 1 plus sine theta, we're going to get 1 minus sine squared theta on the bottom. So we multiply inside the argument of the modulus of the top and the bottom by 1 plus sine theta. And this tells us that the integral of the secant function with respect to theta is a half the logarithm of, and on the bottom we have 1 minus sine theta times 1 plus sine theta, and that's 1 minus sine squared theta, and on the top we have 1 plus sine theta multiplied by 1 plus sine theta again, so that's going to be 1 plus sine of theta all squared. So everything here in the brackets is squared. Now the denominator here, 1 minus sine squared theta, is cos squared theta, so we can write this as a half the logarithm of 1 plus sine of theta all squared over the cosine squared of theta, plus, I should have written integration constants here, I suppose. And now we see that we have a half here, and then inside the logarithm its argument is all squared. This squared over that squared is equivalent to 1 plus sine theta over cos theta all squared. So the squared and the half here cancel, and we have the logarithm of 1 plus sine theta all over cos theta to the power here of 1. And notice that when we took the square root inside here, brought this factor of a half in, we take the square root. It doesn't matter whether we choose the positive or the negative root overall here, because this is a modulus. The modulus means take this ratio and make it positive. So there is no ambiguity about the sign inside here. modulus makes it positive. And now we see that we have inside the argument of the logarithm the modulus of a sum, and we can break this up into two terms. It is 1 over cos theta, but that's just the secant function. So we have the logarithm of the modulus of the secant of theta, sec theta, plus, and then here we have the sine of theta over the cosine of theta, and that's just the tangent function. So sec theta plus tan theta. Close the modulus, add an integration constant. And this is our final result. So what we've seen in this video is that the integral of sec theta with respect to theta is the logarithm of the modulus of the sum of sec theta plus tan theta. And that, with this ambiguity of an integration constant, is our final result. Notice that the argument of a logarithm is a sum of two terms. The rules for logarithms do not let us simplify such a sum, and this is our final result. What we can do, and what we should do, is to check this by differentiating it. So on the next slide, I'm just going to mention that and also talk briefly about another very similar integral. So on the previous slide, we obtained this result for the integral of the secant of theta, and the thing that we should now do is to check that it's correct, and we check it by differentiation. So we should check that d by d theta of the logarithm of the modulus of sec theta plus tan theta is equal to 1 over cos theta or sec theta. So that's, I think, a very good exercise both for using the chain rule for calculating the derivative, and then having done that for algebra using trigonometric functions. The other thing that I think we should do as an extension to this video is the following. So, extension. And that is to calculate the integral of cosec of theta with respect to theta, and that is, of course, the integral of 1 over sine theta with respect to theta. And this integral can be calculated in a very similar way to the integral above, and I think anybody who's fully understood the integral that we've discussed so far in this video will be able to calculate this. And let me just write out the result for you. And what we have is that this is going to be minus the logarithm of cosec theta plus cotangent of theta plus an integration constant. And this can also be written, and this is nice algebra practice to show that this is true, this can also be written as the logarithm of the modulus of cosec of theta minus the cotangent of theta plus an integration constant. So clearly from the rules of logarithms, this is the logarithm of 1 over the argument. That's what the minus sign means. So what we have to see that these two are equivalent is to show that 1 over cosec plus cot is equal to cosec minus cot. And that is, again, nice algebra practice to show that it's true. So these two expressions are two different ways of writing down the integral of cosec. And just as a final remark, the difference between this integral and this integral is that we're going from here 1 over the cosine to 1 over sine. So if we do that, if we replace cosines by sines, then we would expect to get a result which is very, very similar to this one, with cosine replaced by sine and vice versa, but there are often minus signs because the derivative of sine is plus cos, but the derivative of cos is minus sine, and that's what this minus sign here is doing. And I think this is a good exercise for you to do, and showing that these two are equivalent is also a very nice exercise as well. And with that, I'll stop this video.